by writing. After the class, I can take it up.
Okay. Oh, okay, sir. I will paste it in chat window at the end of it.
Yes, yes, you do so. Thank you. Hello. Please confirm that you can see the presentation and hear me. Hello. One of you, please confirm that you can see the presentation and hear me.
Yes, sir.
Okay, thank you. Thank you. Please mute your mic, everybody, now. We shall start. So, here is what we were discussing in the last class. So if you recall, we have started our discussion on physical systems. We have taken some simple systems. We considered some systems which can be described by simple autonomous first order differential equations, like we discussed radioactive decay, we discussed some electrical circuit problem, we discussed a geological or geophysical problem of viscoelasticity. I mean, it's also a problem of the physics of materials. And now we are on a fluid mechanical problem, a fluid dynamics problem. So in this problem, in the last class, we considered the present scenario whereby an object is falling through a very long liquid column. It's all so long that it may practically be considered bottomless, like let's say the ocean depth. Average ocean depths are 5 kilometers. So, and you are dropping some object through a very, very long column of liquid. In this case, it is usual. It should be usual to imagine that it is water. Now, so when an object is falling through a liquid, the very fact that it is falling downwards means that there is gravity acting on it. Fine. But then, in opposition to gravity, there are two forces that act on the same object. And what are the two forces? The first is a standard resistance that you are familiar with, namely upthrust. Upthrust is the weight of liquid displaced. So if the object has got a volume of capital V, this is capital V, then the mass of liquid displaced, I mean, it will displace the same volume of liquid, capital V. V, the mass of liquid displaced will be the density of the liquid times the volume. That is what you have. And then weight will be mass times acceleration due to gravity. So rho L into V into G. So this will be the upthrust. And also, we had some discussion on this point. The fact that an object travels through any fluid medium, like water or air, means that the viscous properties of that fluid will also come into play, in as much as it will offer a resistance to the motion. So if there is no motion, this force will not come to play. So this force, the resistance, is a function of the velocity. So the simplest way we can say, I mean, there is no mathematical proof or any such thing about how we choose this function, I mean, what this function can be. Usually the answer comes from experiment. And so here we are taking a very simple function, namely a linear function. So this viscous drag force. So drag meaning the object is trying to fall through the long liquid column, but the fluid medium is trying to drag it in the opposite direction. So this is known as the viscous drag force. And when we say friction over here, we refer to standard fluid friction. In other words, viscosity. Okay. So those were the points we considered in the last class. That and of course there's another slightly extended point, that if the object that falls through the liquid medium is a sphere, is a spherical in shape, then the drag coefficient. So we have a linear function. So the viscous drag d is a force, and so it will be proportional to the velocity. The proportional constant is k. So usually k is measured through experiments for complicated. Let's suppose you complicated geometry. Suppose you throw in a misshapen rock. A rock doesn't have to have a perfect geometrical shape, right? So it can be any kind of shape. And so you throw it, then you'll have to measure the drag coefficient k through experiments. But otherwise, for a sphere, there is a proper theoretical formula for the drag coefficient. It is 6 pi into eta times r, eta being the viscosity of the liquid and r being the radius of the sphere. I also mentioned the word dynamic viscosity. I'll come to this dynamic word later. Okay, so this linear formula applies well when the velocities are small, right? Such as when what happens when an object falls through liquid. A liquid will offer greater resistance as compared to air. Water will offer greater resistance to any particle traveling through it as compared to air. So in air, it is possible to generate faster traveling speeds. Anyway, so here's the force balance equation. We ended at this point that mass into acceleration is the force. Okay, and there are three terms to the force. First is weight downwards, as indicated by this downward arrow. If you say that the force downward is to be seen with the positive sign, the gravity that is, then the resisting forces must come with negative signs. So buoyancy is acting upward this way, and so is the drag coefficient acting upward. So with this, we have the complete force balance equation, and our task now will be to solve this equation. Let us see. First of all, the mass of the object is its density rho, the density of the falling object, times its volume v. So if I divide this equation throughout by m, so I will have dv dt is equal to g. Okay. And then here I will have rho L into V by M, but M is to be seen as rho into capital V. See, there are two V's over here. One is the V of the velocity. This is a small v. And the other is the V of the volume. This is capital V. But anyway, very soon we shall eliminate this volume business. And so here you have rho L times V divided by M. But M is rho into V, where V is the volume. So this V and this V will cancel, and you'll just have rho L by rho L being the density of the liquid and rho being the density of the object falling through the liquid. Then you have got minus K by M. Okay. So you can see this equation is like V is a function of T. So you have V dV dt is equal to G is a constant, rho L is a constant, rho is a constant, minus k by m into v. Okay, so this whole package, all these free additive constants, I'm writing as g bar, where g bar is equal to g into 1 minus rho L by rho. Okay, so now if you think of it like this, you can see dv dt is equal to constant minus constant into v. And so this is in the form of dx dt is equal to a minus bx, where a is g bar and b is k by m. So immediately you know what the solution of this thing will be like. So at t equal to 0, v will be equal to 0. So you're just at t equal to 0, v is equal to 0, meaning that you're just holding the object. And then at t equal to 0, you just release the object. So initially at t equal to 0, the object doesn't have any velocity. So that is allowed. And so if that allowed in the sense that when x is equal to 0, if a is non-zero, dx dt will continue to be non-zero, and therefore values of x will add on very soon. I made a slight mistake over here. At the time, I mean, this thing should be k by m, because this whole thing will be, I mean, if you recall the solution of this equation, x is equal to x naught being equal to a by b, right? So a by b will be m g bar by k, as I've written with v subscript capital T. I'll come to that thing later. Into 1 minus e raised to minus bt, e raised to minus bt is the integral form. But b is k by m, so by mistake I wrote m by k. It is corrected in the sheet of corrected formulae. So you can just check that thing. So this statement here, it should be k by m, right? Not m by k, k by m. So I've in the correction sheet, you will find that correction mentioned. Okay, so in which now, so let's see now, you have the terminal velocity. This is known as Stokes's law of terminal velocity. Stokes, as in this formula, K is equal, it was Stokes who studied this problem for spherical object falling through a long liquid column. So this formula was derived by Stokes. So this is Stokes's law of terminal velocity. Now, what do I mean by terminal velocity? Very simple thing. When t goes to infinity, kt by m, not mt by k, kt by m, k and m are constant quantities. So when t goes to infinity, this thing will go to zero, and the velocity will go to a maximum value of v subscript capital T. Capital T as in terminal. Terminal meaning the end point. So as I said, these sort of systems, they grow early on in a linear fashion, and then afterwards they saturate towards a limiting value. And the early growth will be linear. What is the early growth? Again, you should have no difficulty finding this. Just refer to our discussion of dx dt is equal to a minus bx, with the initial condition that at t equal to 0, x is equal to 0. So when you have that sort of a solution, um, sorry, just a minute. Yes. So for that kind of a situation, early growth will be linear. V will be proportional to t, g bar t, and after a time scale, so there will be a non-linear, sorry, there will be a time scale, not linear, not non-linear. This is a linear problem, I'm sorry. So the time scale in this, natural time scale in this problem will be b raised to minus 1, or 1 upon b, right? 1 upon b. So 1 upon b is m by k. So t naught is equal to m by k. So V goes to Vt for t going to infinity after this time scale. So before t naught, you'll have a linear growth of V, and after t naught, V will saturate towards the terminal value. And the terminal velocity could also be found from this formula that G is equal to G bar T naught, right? So it's, I mean, you can just check for yourselves here. So if T naught is equal to M by K, so Vt is equal to G bar into T naught. So this is, yeah, so that's how you can write it. Okay. So the initial condition of the fall, as I mentioned, is t is equal to 0, v is equal to 0. If that is the initial condition, then you will get this equation. Now what we will do is that we will go a step further. What we will do is that how is, so far what we have discussed is how is velocity changing with respect to time, right? But now we will also see that how is the depth changing with respect to time. If z is the depth from the starting point, right? Then v is dz dt. Although we are going downwards, we are still saying that greater depth. Greater depth meaning we are taking positive value. Z is positive value. If the surface of this water column is z is equal to 0, of course, anything below it should be negative valued because it's falling below. However, we have kept it positive. Instead of calling z as height, we are calling z as depth. So greater depth meaning greater positive values as we are going downwards. So it's just a matter of just giving it a different kind of a name. Okay, if I had called it height, then I would have had to put a negative sign because anything below the water surface is negative height. But anything below the water surface is positive depth. So that's how it is. So from the starting point, we can write v is equal to dtt of z. Okay, and that is equal to v is equal to, this is our solution, vt into e raised to 1 minus e raised to minus kt by m, right? So, sorry, just a minute. Just a minute, please. Yes. So that error, I'm sorry, has also carried over here. It should be minus kt by m, and this also should be 1 minus e raised to minus kt by m. So at two places you have this error. However, this error is not carried over here after After this, I've written this whole thing as T by T naught. That's how it should be. T by T naught, meaning KT by M. KT by M is T naught is M by K. So divided by T naught. So like that it is. So the integral of this equation will be Z, then V subscript T into dt integrated V subscript T, capital T into T minus Vt e raised to minus T by T naught into dt, and then you have the integral over here. Okay. So let us now carry out the integral. Z is equal to V subscript capital T to small t minus V capital T e raised to minus T by T naught. And then this is standard integral, 1 by minus 1 by T naught. So minus and minus will be plus, and capital C is a constant. So, and then 1 upon T naught will come to the numerator, and you'll have T naught. So Z is equal to V uh, subscript capital T to small t plus T naught into Vt e raised to minus T by T naught plus C. Okay, so when T is equal to 0, Z is equal to 0. So 0 is equal to, this will be 0 plus T naught into V subscript T e raised to Z. 0 is T plus constant. So C is equal to minus T naught Vt. Okay. So when you put this thing together here, you collect all terms containing Vt into T naught, and this is your final integral solution. Z is equal to Vt into T plus Vt into T naught into e raised to minus T by T naught minus 1. So this is one equation, integral solution that we have got. I mean, we can work with this thing, but we're just making our task a little simpler. What we shall do is that we shall rescale this equation just for simplicity of understanding the mathematical part of it. And how do we rescale this equation? Very simple. First, we define a new function zeta, as in the Greek alphabet zeta. Zeta we define as z divided by vt into t naught, right? This is t subscript 0, t naught. Z is a length. V into time is also a length. So zeta is a dimensionless quantity. So when you have this thing, we divide the z by vt into t naught is equal to then t by t naught plus vt into t naught will be 1 into e raised to minus t by t naught minus 1. Okay. And then t by t naught we define as another variable tau. Tau is equal to t by t naught. So now you will see this will become zeta as here plus t by t naught is tau minus 1 plus e raised to minus tau. So this equation looks a lot more compact to work with. Let us now try to plot this equation. Of course, you can always use a graph plotter to plot it, but it's always a good thing, good practice to be able to plot all these functions by hand. So let us see how we can plot this thing. Here is what we shall do. First, we'll take the derivative of zeta with respect to tau. D zeta, d tau is equal to 1. This minus 1 will give you 0. Then d tau of e raised to minus tau. So minus e raised to minus tau. So when d zeta, d tau is equal to 0, what is the condition that we will get? When tau is equal to 0, so it means that d zeta, d tau is equal to 0. You'll just have e raised to minus tau is equal to 1, right? And so that can only be 1, meaning when tau is equal to 0. So you can see this thing will be 0 when tau is equal to 0. E raised to 0 will be 1, 1 minus 1 is 0. So the left and the right hand sides will balance each other. Now we shall look at the second derivative for tau equal to 0. d2 zeta d tau squared will be equal to, take the second derivative of minus e raised to minus tau will be equal to e raised to minus tau. So when tau is equal to 0, d2 zeta d tau squared is equal to 1, which is a positive number. Hence, conclusion is that tau is equal to 0 is a minimum point, because its second derivative positive, meaning that it's a stable turning point, right? And zeta will increase monotonically. So because after that, there is no other turning point. You just have one turning point. And after that, z will increase. Z will increase, of course, it will increase because as time increases, depth will also increase. So any tau or t positive values, z will keep on increasing monotonically. It is not as if that after the object falls through a liquid column, of course, velocity will increase. You have seen this thing. Velocity will keep increasing. There was a misperception at one point of time. And in fact, this misperception is also to be found in a science fiction novel titled 20,000 Leagues Under the Sea by the French author Jules Verne. So there, the idea was that just like, in the case of air, we see that air has got greater density closer to the surface of the earth than, let us say, very great heights. Let's say above Mount Everest, air is much less dense as compared to air in your room right now. Why so? Because gravity is trying to pull down the air particles, and more air particles will gather per unit volume on the surface of the earth than above Mount Everest. As a result, when you have to go mountain climbing to very great heights, you have to carry an oxygen cylinder. So it was thought that the same thing should happen to liquid water also. So ocean depths are something like 5 kilometers. So it was thought that at great depths of the ocean, water density will increase because of the higher columns of water above. So suppose some object is falling through water, there will come a stage when at very great depths, the density of the water will be higher than that of the density of the object. And as a result, the object will become suspended somewhere in the middle of the ocean depths. So that was what was thought. And so the author of this science fiction novel wrote that as they were traveling in a submarine, they saw ships suspended in mid-water, just like you can have things suspended mid-air. So ships can become suspended mid-water, but actually no such thing happens. For instance, the Titanic sank right to the bottom of the Atlantic Ocean and settled on the seabed, on the ocean bed. So, and that depth will be something of the order of 5 kilometers. So it's a great depth, of course. So what is the whole idea? That why are we discussing this? We are discussing this to show that the density of water does not change. As a result, so whatever starts sinking through, whatever will sink to the bottom of a glass full of water, a coin or whatever you want to put in, right? Anything that sinks, coin or nail, a heavy metallic object, let us say, whatever will sink to the bottom of a glass full of water will also sink to the bottom of the deepest ocean. So that is what it is. So yeah, so what we shall do is that we shall show that that is exactly what happens. That as time increases, z will increase. Z will not stop to any terminal limiting value, and there will of course be no turning point. So the only turning point is when t is equal to 0. That is at the start. Thereafter, z will keep on increasing monotonically. So let us see, we will now plot this function, zeta as a function of tau. First, we have realized that at tau equal to 0, there is a turning point, which is a stable turning point, a minimum turning point. Second thing, we'll have to now plot the function tau, zeta as it depends on tau for small values of tau and then for large values of tau. Let us see how. So when tau goes to a very small value, nearly 0, but not exactly 0, you can carry out a series expansion of this e raised to minus tau part. So zeta will be equal to tau minus 1 plus e raised to minus tau, which I'm writing as 1 minus tau plus tau squared by 2 plus etc. Since tau is very much less than 1, it's nearly equal to 0, you can neglect the higher orders for tau very much less than 1, but don't neglect the second order because the first order will cancel. You have tau minus 1 plus e raised to minus tau, which is 1 minus tau plus etc. So this tau minus 1 and this 1 minus tau, they will cancel and you'll just have zeta is tau squared by 2, which is a parabolic behavior, right? And let's see. Then alternatively, you can also find this thing for small t, v is g bar into t. I just mentioned to you earlier, v is g bar into t. If that is so, you can find the same conclusion from here as well. dz dt is equal to g bar t, right? V is equal to dz dt. So if you integrate this thing, z is equal to g t squared by 2, which is same thing as a parabola. So this happens, Parabolic dependence of the depth with respect to time happens because in the early stages, velocity is a linear function. But then what will happen when velocity, I mean, so for a long time, when time is long, let us go back to our equation over here. When t goes to, sorry, here, when t goes to very large value, large as in much greater than 1, 1 is the scale here, right? 1 is the scale here, meaning t naught is the scale. If t by t naught is equal to 1, that sets the scale for tau, which means if whatever is scale for tau as 1 will be t naught for t. Okay, so now, when t goes to very large values, or tau goes to very large values, e raised to minus tau will be negligibly small. E raised to a minus a very large number will almost be zero, going to zero. So zeta will be practically of the order of tau. Tau is very large. You can even ignore the 1 against tau. So if that is so, then when t goes to infinity, zeta is nearly equal to tau, which is a linear, and you can also find this thing from the velocity equation somewhat differently. For very large values v of time, v goes to a terminal value vt. So in that case, dz dt is a constant, right? If dz dt is a constant, then dz dt is this constant v subscript t, so z is vt. So you can see z is showing a linear behavior. Z Vt into t, and zeta is tau. So z and zeta are the same, except that there's a scaling factor like this, z by vt into t naught. So if you have to plot this thing, here you plot zeta along the vertical axis, tau along the horizontal axis. Tau is equal to 1 is the transition point. Before that, you have this parabolic second degree dependence, tau squared by 2, and it should have gone on along this dotted curve, but it doesn't happen that way. It switches over to this linear behavior where velocity is constant. Of course, when velocity is constant, dz dt or d zeta d tau will be a linear function. And so at tau equal to 1, you have a shift from one power law to another. So here you have a second degree power law, power dependence of tau squared, and beyond this point you have a first degree power law, tau depends power of tau raised to 1. So this is what you have. Anyway, so as you can see, z or zeta does not stop anywhere. It just keeps increasing to greater and greater values as t or tau increases. So there is no turning point. Once an object has been released in a long liquid column, it will keep falling. It will keep falling, but it will do so with a constant velocity eventually, which is the terminal velocity. Initially, it will accelerate. As a result, Z will have a parabolic dependence. But beyond a point, the acceleration will no longer happen very significantly. You just have a constant terminal velocity. So this thing can also be seen. So as I said, we are discussing fluid problems, right? With a very simple example of objects falling through air, sorry, a long fluid column. So we have so far discussed the problem of an object falling through a long liquid column. So what about an object falling through air? Very long jump. So free fall of a parachutist. How different will this discussion be? Will it be different, this whole discussion? Well, the answer is somewhat different in certain major respects, but in certain other respects, the principle of what we have discussed so far will still carry over. Let us see. So far, we have talked about an object falling through liquid columns, such as water falling through great ocean depth. And now we shall talk about an object falling through air. So let us see. First, in order to do so, we'll have to understand the nature of viscosity of air. As I said, uh, whenever something falls through a fluid medium, just by the fact that the falling object has a velocity, it will encounter resistance to its motion because of the viscous properties of that fluid medium. Note, I'm using the word fluid. I'm not saying liquid or gas. Generally, Both liquids and gases are fluids, except that there's a major point of difference. In the case of a liquid, the density is always constant. Just a while ago, I mentioned to you that the density of water at the depths of the ocean will be the same as the density of water very close to the surface density. But in the case of air, gas, the density can vary, right? So, for instance, atmospheric density is greater close to the surface of the Earth, near the surface of the Earth, than at the top of Mount Everest. So that is one major point of difference between the two fluids. One is, as a result, you call air or gas a compressible fluid. Compressible meaning you can compress them. But water can't be compressed. Water is an incompressible fluid. As a result, its density is a constant quantity. And incidentally, this incompressibility is a property that is applied in the mechanical systems of hydraulics. If you were a mechanical engineer, this thing is very useful. Hydraulic press, or in cars, you apply hydraulic brakes, right? Brake fluid and all those things. If you have good knowledge of automobile engineering, if you're an amateur enthusiast of how a car is manufactured, you would know how hydraulic brakes operate. So that exploits the property of incompressibility of a liquid. But air is not an incompressible fluid, it is a compressible fluid. So if that is so, that being a major point of difference, how will it affect the basic physical properties? So far, I have been telling you all the while that whenever an object falls through a fluid medium, it encounters resistance to its motion because of friction through that medium. That friction, fluid friction, is viscosity, right? Friction or viscosity in a liquid. Here we have talked about a liquid, but it is also there in gases, in air, for instance. So we shall now have to look at this thing. What is the nature of the viscosity or the friction or the resistance offered against the motion of an object traveling through air? Incidentally, in the last class, I mentioned that this resistance that air can offer is not negligible. It is a considerable resistance. The faster you travel, greater will be the resistance. So much so that objects coming from outer space, meteorites, anything that they enter, meteors, these things that they enter the Earth's atmosphere, they travel very fast at the speed of something like 30, 40 kilometers per second. 30, 40 kilometers per second, right? That's a very fast traveling speed by our standards. And as they travel through air, the friction against their motion offered by the air medium actually burns them up. So, as you can see, although you say thin air, the resistance that it can offer is a considerable one. So the question is that we shall now have to look at the nature of the viscosity, the resistance that is offered. In order to understand that, we'll have to look at a phenomenon that you would have heard of. It is known as turbulence. If you are a regular aeroplane traveler, air traveler, you travel in a plane, occasionally you would have come across this situation called turbulence. What is that? It doesn't happen when the weather is good. Cool air usually doesn't have turbulence, but in the summer months during the monsoons, when there is a lot of humidity in the air and there are great air currents carrying clouds, all those things, air shows a lot of turbulence. And what is turbulence? Turbulence is a property whereby certain zones, certain regions in air, turbulence is actually present in a fluid medium. In water also it is present, but it is more difficult to create turbulence in water than in air. But it is there, right? I'll just briefly discuss this feature. Um, so turbulence is a zone where suddenly there is good, a good deal of chaotic motion in the air. For instance, if you are sitting in your room and you've opened the window, a nice breeze is coming in. So that is just the motion of air. Breeze is not exactly turbulence. Turbulence is like an eddy. I'll just give you a simple example of what a turbulent eddy can be like. Um, If you see, let me just discuss diffusion a little. Diffusion of certain material through a fluid. Um, you want to have coffee, let us say, but you want to sweeten your coffee. So you put a sugar cube in your coffee, right? So the thing is that the coffee will be sweetened. If you wait long enough, the coffee will be sweetened on its own. Gradually, what will happen? Molecules of sugar will peel off the cube and gradually blend into the coffee. So if you wait enough, long enough, for an hour or 2 hours, um, the sugar cube will ultimately dissolve in the coffee on its own. You don't have to do anything. But by then, your coffee will become cold. You would be late. You are in a hurry to go to work or to your class, whatever. So what do? You don't wait for the sugar to dissolve into the coffee on its own. You take a spoon, you put it into the coffee cup, and you stir the coffee liquid. Right. As a result, the liquid starts roiling round and round, going round and round. You would have done that thing, I'm sure, when you know, or you want to dissolve sugar in tea. So you stir the liquid medium. So once you stir the liquid medium, it starts going round and round in the cup, and that is an example of turbulence. So it is not a net motion from one part of a region to another, such as in, let us say, the flow of water in a river. So there is net displacement of the fluid material in the flow of river or in an airflow, in a breeze or a wind. So there is net displacement of the material of either air or water from one point in space to another in flows. But here it is just going round and round in a vortex, right? In the case of turbulence, round and round in a vortex. And so in your coffee mug, you have created that vortex by using your spoon and stirring the liquid medium in the coffee mug. That is an example of turbulence. Now, why did I give you this example? Because diffusion, diffusion is a fluid property. I'll just give you some examples. Suppose you want to you want to make your room fragrant, right? So what you do is that you spray perfume in one corner of your room. And if you wait long enough, the perfume molecules will slowly diffuse through the air in your room and eventually reach the opposite corner. So initially, when you spray the perfumes, your friend sitting at the opposite corner will not be able to get the fragrance. But eventually, after some time has passed, the fragrance molecules, the perfume molecules would waft through the air and reach the other end of the room where your friend will be able to smell the fragrance. Now, this is a property of diffusion. Now, you can enhance this, expedite this diffusiveness by doing a few things. For instance, if the air is hot, then the air molecules will be traveling faster. Hotness means average kinetic energy is higher. So if the air is hot, the air molecules will be traveling faster. And if they're traveling faster, they'll be bumping the perfume molecules that much faster. And as a result, the perfume molecules will be forced to move that much quicker. So temperature has a role to play in diffusion. Also, if you're saying that, oh, well, I don't want, I'm inviting guests and they are due to arrive in just 5 minutes, and I want this room to smell nice. So what do? You start fanning the air with a newspaper or whatever. You can even start the fan on, and so you will create turbulence in the air contained in your room. The fact that the fan starts moving means that it will start disturbing the nicely settled, quiet air, and this whole disturbance business will create a lot of turbulence in the air, and this turbulence will enhance the diffusion process of the perfume molecules, and that the diffusion will happen that much sooner. I'm talking about diffusion with it for a reason. So just bear with me. So similarly, you also enhance diffusion in your coffee mug. You are in a hurry to go out. You can't wait for 2 hours for the sugar to dissolve of its own accord. So what you do is that you take a spoon and stir the coffee liquid. As a result, the sugar is dissolved that much faster. It will also help you if the coffee is hot. Once again, you can see temperature enhances diffusion, and by the fact that you're also disturbing the liquid, creating a lot of turbulence in the liquid, that is also enhancing the diffusion. Now, diffusion is a property, is an inherent property of the fluid material, right? Certain fluid material will allow faster diffusion, certain will allow slower diffusion. It depends on the density of the fluid, its molecular structure of the molecules, all those things. Those things are there. But it's still an inherent property of the fluid. But you are enhancing diffusion by creating turbulence or heating up. Heating will also create turbulence, right? So it is that viscosity is an inherent property of the fluid. In the case of water, viscosity is strong because water is a dense liquid, dense liquid. I mean, much more dense than air, of course. But then another liquid like honey or tar, they are even more viscous than water. So different liquids will have different viscosity values, right? And so it is gases will also have viscosity values, but gas is a very thin fluid. Also, it's a compressible fluid. So the viscosity offered by a gas or the fluid resistance, fluid friction offered by air will not be as high as that of a liquid. However, now you follow this point carefully. However, just like diffusivity, which is an inherent property of a liquid, can be enhanced by creating turbulence, so it is that viscosity of air, which is an inherent property of fluid air, can be enhanced by creating turbulence. And as a result, when you have hotness, you also have turbulence. Just a while ago, I gave you an example. On a cool winter morning, the air is quiet and is not disturbed too much. So, if you were a pilot flying a plane on a cool winter morning, you would not encounter too much turbulence. But a very hot, humid weather, hotness will cause a lot of air to go up and come down on the other side, set up large convection cycles. It will set up large pockets of turbulence where the air will be roiling around, moving in fast eddies. So if your plane were to get into that kind of an air pocket, you will realize that the plane is being jerked around a lot, rattled around a lot. So that is not a very pleasant experience for those who are frequent flyers. But that is unavoidable. If you have air, there will always be some pocket of turbulence or the other somewhere. So turbulence, as I said, is a common phenomenon in the atmosphere, as I've written over here. And turbulence, although see, atmosphere is air. Air doesn't have a very high viscosity of its own. However, turbulence will enhance that viscosity in a, sorry, just a minute. In as much as turbulence enhances another inherent property of a fluid, namely diffusivity. I just gave you a common example of that. You want to dissolve sugar in coffee or tea, you create turbulence to make the dissolving process happen that much quicker. Now, here we are looking at the word dynamic viscosity. Earlier, I told you that I will come to this word dynamic viscosity. The dynamic viscosity is written by the symbol eta here. Now, there is another viscosity. It is known as the kinematic viscosity. Kinematic viscosity is eta divided by the density of the fluid, and it is given by the symbol, written by the symbol nu. Nu is equal to eta by rho. Okay. Um, so if that is so, now in the case of a liquid, water, for instance, I said that they are incompressible fluids, meaning that their density does not change. So rho is constant for a liquid, but for air or a gas, rho is not constant. So nu will be equal to eta by rho, where this rho is also a variable quantity. Okay, so atmospheric turbulent eddies. Eddies are these zones where you have a lot of vortex-like motion. Incidentally, in a cyclone, if you have seen satellite images of cyclones, so we are experiencing cyclones quite frequently these days, both in the Bay of Bengal and in the Arabian Sea, more in the Bay of Bengal than in the Arabian Sea, though. So if you have seen satellite images of cyclones, you will see that there is this vortex-like behavior. So immediately you know that that's a very large-scale eddy, turbulent. Eddies are these zones, pockets where you have this vortex-like motion going round and round. So these turbulent eddies have a characteristic length scale of L. For instance, if you have stirred coffee in your coffee cup, the characteristic length scale of the eddy that you have created, turbulent eddy that you have created in the coffee liquid will be of the diameter, will be of the order of the diameter of the cup, right? The vortex that you have created can't be any larger than the diameter than what the cup can fit in. And on the other hand, it can't be too small either because you are stirring the coffee with your spoon on the largest scale, which is of the order of the diameter of the coffee cup. So it is, or if you're talking about a cyclone, that's also a good deal of, there's also a good deal of turbulence in a cyclone. The diameter of a cyclone is typically of the order of something like a few hundred kilometers, right? Or maybe you can also see turbulent eddies in small scale tornadoes. Tornadoes are more frequent in America, not so much in India. Here in India, we have very large scale cyclones, right? So these things, so these turbulent eddies have a characteristic length scale. So typically that's of the order of the diameter of the largest eddy. So that is what you have. And so here, and apart from that, there's also a characteristic velocity with which this round and round vortex motion is happening. In the case of your coffee cup, the velocity will be the speed with which you are pushing the liquid around with your spoon, right? In the case of a cyclone, that is the of the order of the wind speed of the cyclone, something like 150 kilometers an hour, something like that. So that those are the length and the velocity scales of a turbulent eddy. Just to give you some example, there is an idea known as Reynolds number. Reynolds number, sorry, I just made an error over here. There should be no apostrophe over here. It is just Nolds, right? Reynolds number. So this Reynolds number is defined as, well, symbol is R subscript E, Reynolds number is defined as length times the velocity of the eddy divided by the kinematic viscosity, right? So that is defined as Reynolds number. Now length into velocity, and this thing nu is equal to eta by rho. Now this nu has the dimension of L squared per time. What is this thing? How will you be able to find out? There's no difficulty in finding this quantity out because I told you how do you define the this quantity, the dimension of eta. Eta is into dV dz is equal to force per area, stress, right? So stress is force per area. You can find the dimension of force. Force is mass into acceleration. So m into L t raised to minus 2, m L t raised to minus 2 divided by area is L squared, and that is equal to eta dV dz. So eta dV dz will be L per time by L. So basically, you will have the dimension of eta. I leave that as an exercise to you. If you recall our previous discussion when we talked about viscoelasticity, I told you force per area is stress, and that is proportional to dV dz, which is the velocity gradient, and the proportional constant is eta. So force per area is equal to eta into dv dz. dv dz will have the dimension of length per time per length. Force has the dimension of mass into acceleration. So m into L t raised to minus 2. Area has got the dimension of L squared, right? So m L t raised to minus 2 by L squared is equal to eta times L t raised to minus 1 by L. So from that, you can find the dimension of eta. You can check these things for yourselves. And nu is eta by rho. What is the dimension of rho? Mass per volume, m L raised to minus 3. You can check that dimensionally eta. It's a simple exercise. You can do these things by yourselves now. So you can check that dimensionally nu will have L squared t raised to minus 1. Basically, L squared t raised to minus 1 is L into L t raised to minus 1. This is what will happen when you multiply length with a velocity. So nu dimensionally is like a length times a velocity. And in the numerator also, you have a length times a velocity. So length times a velocity dimension divided by another length times a velocity dimension, meaning the Reynolds number is a dimensionless number. Okay. So in the case of water, the kinematic viscosity, which is the dynamic viscosity by density, is 10 raised to minus 2. This discussion is now important. Follow carefully. 10 raised to minus 2 in the case of water. Nu for water, liquid water. Nu for air is 10 raised to minus 4, both in the SI system. Length into meter per second, meter into meter per second. So you can see the kinematic viscosity of air is much less than that of water. Okay, so here is how this discussion is relevant. For any object traveling through a fluid medium, which is can either be air or water, the fluid drag is generally written as d, which is the fluid drag force, proportional to velocity raised to gamma. Gamma is an exponent. Now you follow very carefully what I'm saying. What is the value of gamma? When the Reynolds number is of the order of 10, LV by nu, Reynolds number is of the order of 10. And how can you have this kind of, see, how will you control Reynolds number? Low velocity, high kinematic viscosity. If you have that thing, then Reynolds number will be small. High velocity, low kinematic viscosity. Reynolds number will be large. As you can see in the case of water, kinematic viscosity is much larger as compared to air. So, and when you're traveling through water, when an object is traveling through water, the velocity with which the object is traveling will be less. Simple example, a submarine and an aeroplane, both are driven by an engine, equally powerful engine, except that an aeroplane will travel much faster because it is traveling through air, whereas a submarine will travel comparatively much more slowly. That is the whole idea. So why? Because water offers greater resistance. So when something is moving through water, the velocity scale or the equivalently the turbulent scale in velocity scale, that will be small. Mu will be large. So Reynolds number will be less for water as compared to air. In the case of air, the kinematic viscosity is low, denominator is small, therefore overall it will be a large number, and the velocity is also large because things can travel faster in air. Turbulent velocity eddies will have a faster characteristic value, all those things. So here's the answer. Low V, high nu, Reynolds number is of the order of 10. And in that case, it is an experimental fact. There's no theory behind it. In that case, gamma is equal to 1. Okay. If gamma is equal to 1, then D is proportional to V raised to 1, first power of V. Now, when the Reynolds number, sorry, I made another mistake. There should be a subscript E over here, right? Subscript E to the Reynolds number here. When the Reynolds number is between 10 to 1000, one really doesn't know what gamma to use. One has to look into experiment. There's no clear-cut prescription. That is what I am saying. Gamma is a little uncertain. But when Reynolds number is 1000, and that largeness This large value can be achieved when you have high velocity and low kinematic viscosity. When that is of the order of 1000, high velocity and low kinematic viscosity, gamma is equal to 2, as in the case of air. So gamma is equal to 1, as in the case of liquid, and gamma is equal to 2, as in the case of air. And this happens due to turbulence in the air. Turbulence has enhanced the resistance of the air against motion of an object through it. So when you have liquid, gamma will be equal to 1, d will be proportional to the velocity raised to the first power, and this is the formula that you shall use. D is proportional to velocity raised to the first power. You apply a linear function, d is proportional constant into v, k is the constant of proportionality. But if you are talking about air, then d will be equal to k into v squared. So you have a parachutist falling from a height. Now let us discuss this thing. So remember that thing. If an object is falling through a liquid, I held this long discussion just for you to have a clear idea of something. When an object is falling through a liquid, as in water, the drag force is proportional to v raised to the first power. So d is equal to k into v. When an object is falling through air, the drag force is proportional to v squared. Therefore, d is equal to kv squared. Okay. So when you have a parachutist falling from a height of 32,000 feet to 20,000 feet, that's how all these skydiving, or I mean, skydiving, it doesn't happen at very great height. But people are setting all these world records. They jump from great heights, and then they initially go through a stage of period of free fall through air. And then when they come very close to the ground, they open the parachute. It's not correct to open the parachute at a very great height, because then the parachute will be blown away by the wind, and you will not be arriving at the target point below. So it is parachuting. In the case of parachuting, first you undergo a free fall, get as close to the target point on the ground, and then at a height of around 2000 feet, you open the parachute, and then slowly you fall. So here what we shall consider is the free fall stage of paradiving, right? So some parachutist has jumped off a plane 32,000 feet. 32,000 feet is actually a great height, because the height of Mount Everest is less than 30,000 feet. It's 29,000 something, whatever feet. So slightly less than 9 kilometers. So 32,000 feet is actually higher than Mount Everest. So you jump from, if you're a parachutist, you'd first jump from that great height from an aeroplane, fall freely to a height of about 2,000 feet close to the ground, and then you open the parachute. So what is the dynamics, the force balance equation from this height of 32,000 feet to 2,000 feet? You take the resistance to be k times v squared. D is equal to kv squared. And once again, as I said, the drag will be proportional to v raised to gamma, and so gamma is chosen as 2. So the drag constant, the proportional constant, is k. D is equal to kv squared, and so the drag coefficient is that proportional constant. K is greater than 0. So there is no formula as in that Stokes formula of a spherical object falling through a liquid. So K is equal to 6 pi eta r. This thing applies to a spherical object only falling through a liquid. Make no mistake about applying it to other scenarios. Sphere and liquid. Only then you have this formula to be applied. Otherwise, K is usually measured through experiments. Okay, so now let us see what happens. So you basically then have a dynamic equation. The force balance equation will be mass into acceleration m ddt of v is equal to mg, which is gravity. And then this is the air drag resistance minus kv squared. You are not accounting for buoyancy in air, which is not a very significant effect, as in the case of water. Why is it more significant in the case of water than in the air? Simple answer: density of water is much greater. As compared to that of air. So that's why this number will be large in the case of a liquid. That's why you have to account for buoyancy. But if it's air, density of air is very low. And so you neglect this quantity. So it's just mg minus the drag. But in the case of air, the drag will be minus kv squared. So those are the two major points of difference. First, in the case of a liquid, the drag resistance is minus kv. In the case of air, it is minus kv squared. In the case of a liquid, you also have to account for buoyancy, rho L Vg, but in the case of air, you neglect this thing almost to be almost equal to zero. So you just have mg minus kv squared. So let us now look at that equation. So what you do is you divide this equation by m, and dv dt is equal to g minus k by m v squared. Okay. And this equation is now in the form of dx dt is equal to a minus bx squared, which we have discussed earlier. We have discussed already, right? We discussed earlier, where a is g and b is equal to k by m. Okay. So now applying all our earlier knowledge of solving an equation, like this is a nonlinear equation, this is no longer a linear equation. So far, what we have discussed before we took up this problem of free fall through air, free fall of a parachutist, whatever, through air, before this, all we have only worked with linear equations, linear differential equation, autonomous linear differential equation, as in A minus Bx, or like in the case of the viscoelasticity problem, this is the same equation that we applied. Similarly, for the circuit problem of QRC circuit, this is the same equation that we applied. In the case of the radioactive decay problem, it was simply minus lambda x. So far, the right-hand side had an autonomous function, which was a linear function. So now we are looking at a very simple example of a nonlinear function. Here, this is the equation of a parabola. A minus bx squared is the equation of a parabola. So that's not the equation of a straight line. So that's not a linear function on the right-hand side. But we have solved a mathematical function like this. So all that we discussed over there, we will simply bring forward over here, saying that at t equal to 0, v is equal to 0. And that is how it happens. A parachutist, what does the parachutist do? As soon as the plane door is open, the parachutist simply just quietly steps out and just suspends momentarily in air and then starts falling down, right? So initially the velocity is 0. So t is equal to 0, v is equal to 0. That's the initial condition. And that applies here also. If initially v is equal to 0, dv dt is equal to g still. As a result, even though you're starting with a 0 value, dv dt has got a positive value g, and so velocity will immediately start increasing as time goes. So that is, and this is the integral solution. This integral solution we got when we solved dx dt is equal to a minus bx squared, right? So what is a? A is equal to g and b is equal to k by m. So the integral solution is square root of a by b. Please recall that thing. Square root of a by b will be g divided by k by m. So that is mg by k, square rooted over, of course. And then you have this tan hyperbolic function. This is the time scale. Inverse of this is the time scale. Square root of m by kg is the time scale. So that is what you have. When t goes to infinity, this tan hyperbolic function will go to 1, and v will go to the terminal velocity of square root of mg by k. Okay, recall that thing. And when t goes to 0, you will have a linear function. All of these things we have discussed when we discussed dx dt is equal to a minus bx squared kind of a system. So all of these things we talked about in our mathematical theory class, so we don't have to repeat all those things uh, again. I'm just applying all those ideas, just making a note that a is equal to g and b is equal to k by m. We can recover all our results from there. So when in the early stages, t tending to 0 but not exactly equal to 0, the velocity can be found out that the early growth will be a linear growth. V is equal to gt. Okay. A natural time scale of this problem will be square root of m by kg. Please just check your mathematical discussion. And so the early linear growth will change over to a saturated growth over a long time. Velocity will uh, go towards a limiting saturation value of mg by k square rooted over on a long time. And the transition from this linear behavior to this saturation will happen after a time scale of square root of m by kg. Just note that here it is square root of m by kg, but in the case of the liquid problem, the terminal velocity, sorry, here, the terminal velocity will be mg by k. But in the case of the liquid, it is square root of mg bar by k here, because g bar is slightly qualified because of this buoyancy business. Incidentally, I hope you are familiar with this formula. You see this thing? If you look at this formula on the right hand side, g into 1 minus rho L by rho. Let me just touch upon this one point. Maybe I should have done that earlier. Just please bear with me. G into 1 minus rho L by rho. If rho L, that is to say that the density of the liquid is less than rho, which is the density of the solid object falling through it, then rho L by rho will be a number smaller than 1. 1 minus a number smaller than 1 will be a positive number. So G bar will be G into a positive number smaller than 1. So it will still be a positive number, although it will be less than the usual acceleration due to gravity. So the object will keep going down, but not with the same acceleration. The acceleration will be less because, and I hope you recall your school knowledge of Archimedes' principle. If rho L is equal to rho, then this will be equal to 1. 1 minus 1 will be 0. G into 0 will be 0. So no effective acceleration downwards. What will happen to an object whose density is equal to the density of the liquid? If you put such an object on the surface of that liquid, that object will not go down. It will just remain suspended over there. You push that object downwards, it will just remain suspended where it is. No going upward or downward. However, if the density of the liquid is greater than the density of the object, then so rho L by rho will be a number greater than 1. So 1 minus a number greater than 1 will give you a negative number. So negative number into g, now you have g bar as a negative acceleration, meaning if you put an object whose effective density is less than the density of water and you force that object deep into the water, you may force it down with your hand, but as soon as you release your hand, that the object will immediately bob up and come up and float on the surface. Why? Why will it come out? Because now it is suffering a negative acceleration due to gravity. The object is being forced upwards, right? So this is what this formula means. Anyway, but whatever it is, it's mg bar by k. But here, in the case of long fall through air, it is not mg bar by k, it is square root of mg by k. Where is the square root coming from? This square root is coming from this square. When this thing will be 0, when velocity tends to a constant quantity, acceleration will be 0. Acceleration will be 0, meaning mg minus kv squared will be equal to 0. Therefore, v will be equal to mg by k square rooted over. That will be the terminal value, mg by k. Anyway, so there is another fluid motion problem that we would now like to discuss. That is bicycle motion against air resistance. Earlier, in this problem, it is long fall through air. An object is falling vertically through air, coming down along the z-axis. And now you have bicycle motion through air, meaning a bicyclist is traveling on a bicycle, pedaling fast, and as the bicycle is moving with the passenger on top of it, uh, air resistance is taking place. So this is now not vertical fall, free fall through air, but this is horizontal motion through air, horizontal motion on the ground, but against air resistance. There will also be a little bit of friction offered by the ground, but that is not what we want to look at. But before we discuss this thing, we need to get back to some mathematical idea. That is what I shall do now. Okay, so I'll stop the sharing. Please just bear with me. Please just bear with me. I'll just start a mathematical discussion. I'll stop the sharing. Incidentally, just a minute. Just a minute, please. I'll also show you, point out the corrections. I told you that the previous note had some errors somewhere. technical errors. So here in page 8, I told you there were these errors, right? V is equal to Vt into e raised 1 minus e raised to minus kt by m. And similarly for the z equation, dz dt is equal to Vt into 1 minus e raised to minus kt by m. So in that, in the main notes, this was by mistake. I wrote mt by k, but it is kt by m. So please just make a note of this correction. It is there, this correction set in your Google Classroom as well. Okay, so let me now go to the math notes and just a minute. I hope you were able to. Sorry, just give me a minute. Here, I hope you are able to see this new presentation. I hope you are able to see this new presentation. If not, you confirm to me immediately. This is a very simple mathematical discussion. You are familiar with first order ordinary autonomous differential equation. Dx dt is equal to x dot is equal to fx, right? Phase plots of first order autonomous system. What is a phase plot? Phase plot is a very simple thing. It's simpler than what you have done so far. In whatever we have done so far, your task was to write a solution, get a solution of x as a function of t. And how would you do that? By integrating. X is equal to fx dt integral, right? Or rather, I'm sorry, dx by fx is equal to integral dt. Integral dx by fx is equal to integral dt. Or you can do it by the Euler method, where delta x is equal to fx into delta t, and then for every time step you put in the value of f, all those things. Either you do it analytically or numerically. You have to find x as a function of t. Here, a phase plot refers to a situation where you simply just have to take dx dt as a variable, as in x dot, and plot x dot versus x. Let us see. Plot of x dot versus x. It's simpler than that. So here, simpler than integrating, you just have to plot this thing. Suppose I've given you the function a minus bx, where a and b are positive numbers. So I plot x dot along the vertical axis and x along the horizontal axis. Since x is just f is just a function of x and nothing else, it's simple to plot this thing x dot versus x. Let us plot this thing a minus bx, where both a and b are positive quantities. So when x is equal to 0, x dot is equal to a, as in here. When x dot is equal to 0, x is equal to a by b, as in here. This is a straight line, right? And now you follow a little important discussion. If you look at this graph that I have drawn on the right-hand side, this is the graph of x versus t. And this is x dot versus x. Follow carefully, very carefully. If you just understand this point, it will help you a good deal in doing a whole lot of other things. Let us see. If you integrate this equation, you will get this terminal value of x is equal to AB. Early growth will be linear, and then the late growth will saturate towards the limiting value of a by b. Very good. So basically, you're starting from a zero value somewhere, and you are going to this thing. Here, now you notice something. The same situation is plotted over here. As you can see in this graph, x is always growing with respect to time. There is no negative slope to this graph. X is always growing with respect to time, right? Meaning dx dt is a positive quantity. If x is growing with time, dx dt is a positive quantity. Now, what is dx dt? Now, let's come back to this graph. Dx dt is x dot. So anything above this horizontal line, you follow this point extremely carefully now, everybody. Anything above this horizontal line means you have positive x dot, right? Suppose you have started with a certain value of x here, x naught. Here we have started at 0, but it could have started at any other value of x, x naught. You have started at the value of x naught. Follow carefully. Since x dot is positive, for this value of x naught, x dot is positive because x dot is above this horizontal line, meaning x will continue to grow because dx dt is positive. X will grow in time. If x is growing in time, so if you start with this value of x naught, x can only go to larger values of x. So so you start from here, your path is only in this direction. You go this way, you assign an arrow going from the left to the right. And if you have any difficulty understanding this, you can take it up at the end of the class in about 2 minutes. But now you come to this side, right? On this side, beyond this black dot, on this side, the arrow is assigned a leftward direction. Why so? Because here, this x dot function has fallen below the horizontal line. Below the horizontal line, x dot is negative. So here, x dot being negative means that as time increases, x decreases. So if you were to have started from this side, x will decrease and you will reach here. And what is this limiting value? The limiting value is a by b. If you start with any value of x that is less than a by b, you will be attracted towards a by b. Just give me a minute and I will finish this discussion. And if you're starting with any value higher than x, you'll be attracted in the leftward passage to a by b. Suppose here in this graph, you started at a value of less than a by b, so you're attracted towards this. If you had started anywhere higher on this horizontal dotted line, you would have fallen below and gone towards this path. So this point is an attractor point. Attractor point, there are two other terms, fixed point and stable point, but I will discuss this thing in detail in the next class. Incidentally, I'll stop the sharing now. I'll stop the sharing now. We will continue this discussion in the next class. So incidentally, on Friday, you have to submit your second assignment. I believe all of you have submitted your first assignment. I have just briefly looked at it. I don't know why I can see 47 turned in, because I thought that the class size was less than 70. So if two persons are turning in the same assignment, only then can you get 47. Less than 60 meaning the number of turning in should not be more than 35, right? So 30 to 35 should be the number, but I've got 47 turning in. So I don't know why that has happened. I mentioned to you in the last lab that you should only be submitting the assignments one per two students in a group. I don't know why this has happened. Please.
Uh,
Anyways, so I'll
yes,
just,
sir. Yes, sir.
yes,
So some people, like some people turned in without submitting any document. So
okay. So